Yeah. For the camera. Okay.
Can I start now? Can we start a little bit? Hi, everyone. Welcome to the last session of the seminar class. We will have 3 presentations today. We start off with Lucas. So Lucas Hoffman is going to talk about this paper SCALO, which is about brain-computer interfacing. Lucas is the 7th semester bachelor student in computer science, and is currently doing his bachelor thesis in machine learning and computer graphics. So you can continue.
All right. Can you hear me well, everyone at the back? All right, perfect. So welcome to my presentation on SCALO, an accelerator-rich distributed system for scalable brain-computer interfacing. And thank you, Nika, for the introduction. All right, let's start with the executive summary. First, I will go over some problems, specifically those traditional brain-computer interfaces, or short BCIs, are facing. Firstly, they are mostly constrained to a single brain site, which prohibits brain-wide operation. Secondly, they must operate under tight power constraints. And third, often to cope with these previous 2 constraints, they specialize to only a single application, which of course limits flexibility. From these problems, we derive our goals that the authors want to solve with this work. They want to develop a real-time distributed BCI architecture that supports multiple wirelessly connected implants, operates within a tight power budget while ensuring low latency and high throughput, and supports flexibility via programmability in the best case. And for this, the authors present SCALO, a system of wirelessly networked implants for distributed brain interfacing. SCALO provides real-time processing enabled by onboard, per implant, compute and storage, flexibly composable hardware accelerators, efficient resource usage enabled by optimal scheduling, and high-level programmability, allowing users to deploy custom pipelines and algorithms. And now for the key results. SCALO provides increases of up to 10x for seizure detection and movement intent applications, and up to 385x higher processing rates for applications, for all other applications in comparison to state-of-the-art prior work. Then they operate within a 15 milliwatt per implant power budget and are scalable up to 60 implants on a single brain. All right. Here's my outline. I'm sure you're familiar with this by now. So let's go right into the background. So what is a brain-computer interface actually? So a brain-computer interface is a device that collects neural data from the brain, somehow transmits this to a processor, which then classifies this data into movement intent, speech, or other things. And optionally, it can also provide neural feedback to the brain to, for example, mitigate seizures or similar things. All right. So the most important distinction in the field of BCIs is whether we have surface BCIs, which are placed on top of the skull to sense neural data, or implant BCIs, which are implanted into the actual brain matter. And for the remainder of this talk, I will focus on implanted BCIs because they collect much higher quality data, and also because SCALO is an implanted system. Okay. So for BCI applications, I will focus solely on medical applications, simply because most of these implanted BCIs are, or all of them are, still very experimental. So it is not really recommended to implant this into a healthy human's brain. So these are exclusively used for patients with some problem that can be solved by BCIs. Some of which are, for example, enabling communication, restoring speech, controlling prosthetics, artificial vision, and treating neurological diseases like Alzheimer's, Parkinson's, depression, things like that. And for the remainder of this talk, I will focus on seizure analysis and decoding movement intent, because these are the two distributed applications that the authors focus on and present basically in depth. Okay. Next, motivation. Why do we need distributed BCIs? So fundamentally, most interesting processes in the brain, like learning, sleep, also diseases, most things are distributed processes. So they are not constrained to a single brain site, but they are made up of various brain sites communicating with each other. So this is why inherently we want a distributed system for these applications. Then challenges of distributed implants or implants in general. Firstly, we mostly have time-sensitive applications. So you can imagine if a patient has a seizure and we want to mitigate this by providing neural feedback, we have some latency requirements. So we assume, or the authors assume for this paper, tens of milliseconds of latency. Furthermore, we are handling very high data rates. So neurons produce a lot of activity. And here we assume 100 to 1000 megabits per second that need to be handled. Next, no part of the brain must or it may be increased above or by more than 1 degree Celsius. And this gives us power constraints of less than or equal to 15 milliwatts. All right. And finally, we want to ensure flexibility without compromising, or we want to keep flexibility while still meeting those previous constraints. Okay. So now SCALO. First, I will provide an overview. SCALO consists of 7 main components, and I will briefly say something on each and then go into a bit more depth on a select few. First, on BCI, distributed neural pipelines. This is about converting pipelines, non-distributed pipelines, to ones viable in a distributed setting. Then flexible and energy efficient accelerators, per implant NVM storage, and networking, which you can briefly see in this graphic. So each implant has these components. So processor, NVM, radios for communication, and each processor consists of a processor fabric of accelerators. Next, optimal system scheduling and programming and compilation, which allows users like clinicians or researchers to define programs, which are then compiled into a static schedule that optimally maps applications to accelerators. Okay. And finally, system maintenance, which is about clock synchronization between nodes and power supply. So they assume here some wireless charging power supply, but don't go into any depth on that. All right. And now we'll focus on these 3 main points. So first, on BCI distributed neural pipelines. As I said, the goal is to convert traditional pipelines into ones suitable for distributed processing. The main problem here is the inter-node communication bottleneck. And they then present a number of implement optimizations to handle this bottleneck. And I will go over 2 of them. Firstly, decomposing classifiers. So often for neural data, we need to classify the neural activity into, is this a seizure? What kind of movement does the user want to make? And so on. So a naive approach to handle this would be to send all data between the nodes, then do a global classifier on each, or potentially also only one, but the main point is sending this data, and then send the output to the device, the movement, for example. And the optimization they provide is, instead of this, each node computes a local classifier on its collected data. Then this is aggregated on a single node. And these local results that are now sent over the network, instead of the initial data, so the full raw inputs to the classifier, are then about 100 times smaller. So that's where we reduce the network load. And then on this one node, it computes an aggregate classifier, which is then again the same final output, which is communicated to the device. Okay. Next, they use locality-sensitive hashing, which is basically a hashing method that, like regular hashes, provides fixed size outputs, and in this case, reductions in size, but also maps similar inputs to similar hashes. So we can compare the hashes in like seizure detection, for example, and still have some meaning to those hashes instead of the usual cryptographically secure hashes. Okay, and then this is how you would imagine, right? You have a signal, you have this LSH function, you pass it through, and you get a hash that is about 100 times smaller than the initial input. And wherever possible, we only send this over the network instead of the full signal. Okay. Yeah. And now I will present a brief example on seizure propagation analysis, how this may look like. So this would be a centralized setting. And one thing important to note here is that centralized means we have a centralized processor, but we can still have multiple like electrodes on different brain regions, essentially. So we would detect the electrode data, classify, is this a seizure or not, and then compare it to all the other regions. And the pipeline that would work in the distributed setting is this. And what I would like you to focus on is firstly, that we initially only send the hashes when we detect a seizure. Then in the remote device, so in other nodes, we do a collision check on those. We can compare them on similarity measures because they are locality sensitive hashes. And then we only send the full signals for exact comparisons once a match is detected, and also only to the node that has detected the match. Okay. Now for flexible and energy efficient accelerators. So this is this processor fabric that I showed before. Don't need to understand it in detail, but the key ideas here are that each node's processor consists of various processing elements, or short PEs. And these PEs are connected with programmable switches that allow flexible composition of them, basically along those arrows in a sense. And through that, you can define the custom pipelines and have massive flexibility within certain class of applications. Furthermore, each accelerator has deterministic latency and power usage, which allows the optimal scheduling that I mentioned at the start. And they also implement a number of per PE optimizations, first to enable this, but also to gain various power savings and performance improvements. And I would refer you to the paper if you want to know more about that. All right. So now to get back to this example very briefly. So don't be scared. What I want you to focus on is this here, right? So you can see, for example, here the seizure detection, which wants to classify neural data into seizures, uses here a number of like feature extractors, and then puts this through a classifier. And this basically corresponds to a pipeline composed of elements in this sector here. And like here's like hash generation and communication, various things. And this is how these pipelines are built. Okay. Now let's talk a bit about networking. So I will focus on the wireless Intra-SCALO network. There's also one to communicate to external devices, and this switch network, which within the processing fabric, but I will only talk about this. And you can imagine here you have these nodes. Each node has this intra-BCI radio, and that's essentially how they communicate. The packets have header and data, both augmented with checksums. And this is an important point. We keep erroneous signals. So we either transmit signals or hashes. And if it's a signal and the checksum isn't valid, then we still keep it because these signal similarity methods are naturally resilient to a few errors. And I will talk a bit more about that later. Okay. And also we additionally compress hashes, but we don't compress the signal because the increased length makes them more likely to have some errors. And if we compress these erroneous signals, then we lose this resilience to those errors. So we just send the full signal. Okay. Now for evaluation results. First, some things about the methodology. So firstly, all of this is simulated, so this hasn't been implanted anywhere. But yeah, the processor fabric is designed and simulated using cadence tools. There's something cut off here. And NVM is simulated using NVSim. The configurations are each node has 96 electrodes for sensing neural data. We assume a temperature of 40 degrees Celsius, so this is close enough to body temperature in this case. And each node has 128 gigabytes of SLC NAND NVM, which is like the NVM technology per node. And they have 4 kilobyte byte pages and 1 megabyte blocks, and are divided into 4 partitions for various purposes. Then, as I already said, we have a power budget of smaller or equal to 15 milliwatts per node. Then for the datasets and applications, they use annotated seizure data from a patient with 76 implant electrodes for the seizure analysis, and manually sorted spike data from rats and cell simulation models for spike sorting, which is another application that I didn't mention because it's not a distributed setting. But these are the data sets they mention, so they don't mention, for example, what they use for movement intent. But yes, these are the data sets. Then the architectures that are being compared. So they compare 5 architectures. Again, centralized means a centralized processor, but potentially distributed electrodes for sensing. They compare SCALO, which is what I presented, then SCALO without hashing. Central, which is a centralized BCI, and central without hashing, and then Halo plus NVM, so augmented with storage. And this is the previous work of the authors. And they also compare various SCALO pipelines, so like comparisons within SCALO itself. So for movement intent, for example, they compare different classifiers, so neural networks or SVMs. And for signal similarity, they mostly compare hash versus no hash methods. All right. So this is the main graph that I want to talk about. This is the comparison between the architectures. And firstly, the metric that is evaluated here is maximum aggregate throughput per application. And this is essentially the maximum throughput over all nodes, right, aggregated, while only a single application is running. And they get to this maximum by increasing the load, so the amount of data to be processed until a power or timing constraint, so either these 15 milliwatts or the 10 milliseconds latency is violated. And the comparisons here are done on systems with 11 nodes, so 11 electrodes for the non-distributed ones, and for SCALO, 11 of these nodes that I've been talking about. All right. Firstly, most importantly, SCALO outperforms others by at least 10x in most applications. And we can see that this is in fact all of them except movement intent with the Kalman filter. And then this is because they apply an optimization here to, again, reduce the network load, which centralizes some parts of this Kalman filter. And through that, they kind of lose this advantage of the distributed processing. Okay. Oh, sorry. Then we can also see massive benefits from hashing in select applications, specifically signal similarity and spike sorting. And this is because these are the ones that use the hashes, right? I've shown before the signal similarity, which was part of this seizure propagation analysis. Yes, and so here we can see like, yeah, I guess like 100x, like 2 orders of magnitude roughly of increase in maximum throughput. Okay. And finally, the effect of specialized hardware is visible in the comparison to Halo. So these are specifically these applications. You can see Halo doesn't do very well in these. And this is because I mentioned this previous work of them. So it has a similar processor fabric approach, but it doesn't have the specialized hardware for these specific applications. And there we can kind of see what improvement this gives. All right. Then some other results. So I mentioned up to 60 implants are supportable, and this is under negligible thermal coupling. This is because of the fluids in the brain, the temperature increase falls exponentially with distance from or between implants. And with like, they say with their method, they can support up to 60 implants. Then scalability per application depends on method use and power budget. So they also evaluate this with multiple nodes and less power. But the most important part for their applications is both movement intent and seizure analysis scale well up to 64 nodes, but it's not entirely clear how it would work maybe with some new applications that they haven't tested on. Then up to 9 interactive queries per second can be supported. So this would be, for example, a clinician retrieving past seizure signals over a given time interval. This is shown in a system with 11 nodes, just like the architecture comparison, and it heavily depends on the past time interval that you want to retrieve data from and the query type. And also important here is that while doing these queries, everything else should still be running. Okay, then this is what I said with the resiliency, a bit more specific. So for bit error rates below 10 to the power of -5, signals are resilient to errors, and hashes have less than 1%. So less than 1% of hashes actually have an error because they are very short. And this provided by Scalable, the radio they use has this bit error rate, and this allows performance gains due to not dropping erroneous signal packets, right? And also decreases the network load, because we don't need to retransmit stuff, right? So now for the conclusion, I will restate the problems briefly. So problems of traditional brain-computer interfaces, right? The constraint to a single brain site, the power constraint, and the coping with this by specializing to a single application while sacrificing flexibility. The goals, again, we want to support multiple implants, stay within the power constraints while also having the flexibility via programmability. And then again, what Scalo presents as a solution, real-time processing, flexibly composable hardware accelerators, efficient resource usage, and high-level programmability. And again, the key results, we have a processing rate increases of up to 10x for seizure detection and movement intent, and up to 385x higher for the remaining applications, specifically then in comparison to Halo plus SVM, as we've seen. Again, operation within 15 milliwatts per implant, and scalability up to 60 implants. All right. So I think at this point, any questions? Yeah.
So I was still wondering why we need the radio components. So I imagine power needs to be delivered in some way to these chips. So I guess that includes running a cable already. Why do we still need radio communication then?
That's a very good question. So firstly, for power supply, so they do actually assume wirelessly chargeable power supply. But yes, there are also versions also with like a hub maybe or something like that, something external. And the main reason why, so firstly, for this charging, we would only have like, I mean, yeah, we would need to for all the nodes, but we would only have cables from the nodes to this external charging device, but not between all the nodes. And secondly, it's generally not super safe to do everything with wires because it just increases the risk for infection, and also includes like a more involved implanting procedure and stuff like that. So they want to do everything wirelessly, also the charging.
So you mentioned that one of their main requirements was that it had to be able to process the data at low latency and react to things quickly. But then their proposed solution involves like a multi-hop protocol where they have to do multiple rounds of communication over the wireless channels, which are known to be often high latency connections. How is that actually affected? Like, what's the latency like compared to a wired?
So you mean with this multi-hop, you mean, for example, that you first transmit like the hashes and then do like a match back and then the signals back? That's a good question. They don't go into specific comparisons between like two like actually ones that are wired within each other. So I don't know specifically, but they keep within these processing rate goals and latency goals. So this is kind of, so I guess they say, okay, we've achieved this.
Okay.
There's a question on Zoom.
Yeah.
So in slide 13 and 14, you mentioned that the classification is done distributed instead of centralized.
Yeah.
What is the loss in accuracy that you experience with that change?
So I think it's the same thing. Like it's not like an approximate result. I think I don't know it in detail, but I think they compose basically the like partial weights and then the partial results and have the same output in the end. So I think it's the same result as with the full classifier. If that helps. Okay, thank you. So now for the strengths and weaknesses. I'll just see. So starting with the strengths. So this, I think, presents a fundamental contribution to enable a wider range of BCI applications. Because most interesting brain functions happen across multiple brain regions, as I've mentioned. And this is like the first truly distributed BCI with distributed processing power, actually. And as we've seen, this provides increased throughputs for many applications, and therefore potentially enables many new applications that haven't been feasible before. Okay. Then also the flexible and user-friendly like high-level programming interface. So I haven't like tested it, but I think it's already like kind of uncommon, I guess, that something like this is provided. So yeah, researchers and clinicians can define pipelines in languages like MATLAB, so something that most people in the field probably know their way around in a sense. Then also it's transparent and open source research, so data sets and code is provided. So I've mentioned that not all data sets are provided, for example, for the movement intent, but generally most is provided. The results are reproducible and have been reproduced. And there's a clear methodology that they explain in the script and in the paper, and that I also try to kind of compress for you here. All right, then for the weaknesses. So scalability is really a bit questionable because implanting processors into a human brain is just naturally not very scalable. So it's not clear whether 60 implants is enough for everything, if we would gain significantly more if we were to do more implants, and also how feasible it is to even implant 60 implants, and then like at some point, like we cannot scale further, right? At some point, there's just no space, I guess. All right, then the static scheduling. So while this enables the optimal mapping and like deterministically staying within the power constraints, it also requires, right, deterministic latency and power consumption of all components. So this is definitely like a constraint. This also restricts the range of possible algorithms. So for example, you can only use fixed number of iteration loops. So you cannot use the full language like MATLAB. It may also be potentially inefficient in unexpected circumstances. So in a simulation, maybe this isn't the case, but you know, in the real world, maybe something goes wrong and then the scheduler just doesn't work anymore. And in like the same breath, this provides questionable resilience to hardware failures. So if it is just assumed that everything works and then something fails and the schedule can't adapt, then this may pose a problem. Okay, then also no exploration of human in the loop applications. So human in the loop are basically these, what I said with the interactive queries. And while they state they provide like a number of different classes, which this is one of, and they provide an example for each, they don't provide like an in-depth analysis of an example for this one. So this would be a weakness. And then also, so they state this 385x processing rate increase, right? But this is really only achieved in comparison to Halo. which is not designed for the task this is achieved on, right? It doesn't have this hardware support that SCALO does, and runs it just on like a microcontroller that's on the processor fabric. So really, what I would say is that up to 10x across all applications is more accurate than taking a number like this, is what I think. All right. Yeah.
One question I had is, because they're trying to optimize for a low power budget, do they explain which components consume how much power and whether it validates their decisions on the kind of decisions they make for their architecture? Because it seems like there isn't a strong new idea. Like what I can think of is that they need to tailor the architecture for low power budget, but what decisions make it low power budget was at least not clear to me.
Okay. So yes, they do explain some of this. So they explain their choice of what radios they use, how much power this uses. Then they do some adaptations to some processor elements that to basically, first of all, have this deterministic power, power usage, and also lower power consumption. Then, for example, they use non-volatile memory, right, which uses less power and also space than technologies like DRAM or SRAM. And yes, so in the paper they do, like in the methodology, some overview of why they made what choice and how this all comes together.
And do they talk about it analytically? Like, do you have any experiments or like results?
So there's like in the actual...
Is it a qualitative or a quantitative?
So yes, it is quantitative. So they do have like a table of all these processor elements, what kind of power they use and stuff like that. Yes, so they have that, but there's no like in the experiment section, there's no like graphic or something, just this table. Yes. Any other questions? All right, thank you. So now for the discussion. So this kind of picks up on the point I made before. So our implanted BCI is really the way to go, right? So maybe as a first question, are there any like hard constraints that speak against surface BCIs? Anyone got some thoughts on this?
Well, I would think that brain signals are not particularly energetic signals, so it would probably be hard to pick them up externally without having a huge amount of noise.
Yes.
Yeah, I was going to say that, but like there's also a whole bunch of let's say advantages for the surface BCI. So like you could swap out the parts. There's no corrosion, let's say, for example, when it's implanted in the brain. So
yes, that's also a very good point. Any other ideas? Okay, so yes, so first of all, of course, there are many advantages, right? But there are also, yes, hard constraints, right? So signals reaching the surface electrodes are naturally significantly weakened, right? Also with the depth at which you can sense, you can think of like, whenever you have like a better sensor, if you would implant it, you would always get better data, right? There's always some kind of threshold where data just isn't high quality anymore on the surface. So you have poor spatial resolution, especially high frequency signals are distorted by the skull. And you also have potential problems due to movement, sweat, etc. So things like that. So yes, there are indeed some fundamental weaknesses to surface BCIs. So maybe as a next question, Didier would be, so is there something in between? So like not implanted right into the brain, but also not just places on the skull? Any thoughts on this?
Well, I would guess that the technology for the electrodes themselves probably doesn't evolve all too much. So it might be possible to have like, you just implant the electrodes into the brain and just have like some kind of interface on the inside of the skull, which relays information outside wirelessly, and then have all your compute on the outside.
Mm-hmm.
That way the
it's a good idea.
compute could be upgraded separately.
Mm-hmm.
Yeah, I think the way Neuralink does this is that they run the electrodes. So you have the chip on the outside, and the electrodes like go through a hole in the skull, I guess, and then you get advantages for both. So you can have the measurements be more accurate, and also have like electronics, also for the heat, for example, be outside.
Yes, also a very good point. Anything else? Okay, so yes, in fact, there are things in between, and I will come to something similar to the way Neuralink does it as well. So first, partially invasive BCI. So you could, I guess, I don't know like exactly where like the borders of this are, but I'll just put everything kind of in between beneath this. So first, there are devices that are implanted into the skull, so intracortical BCIs, so that are essentially in the skull. Not out the skull, but also not in the actual brain matter, and they like have been shown to allow control over prosthetic limbs in human trials. Also endovascular, which I think is kind of interesting idea. So this is inserted through a blood vessel essentially, so very small devices. And these also have been shown to allow control over a computer in human trials, and also some movement intent success. Next, also, there's this idea of neural dust, which actually the authors of this also mentioned in like a small follow-up paper, which are basically micrometer scale free-floating modes that kind of just are in the brain somewhere and are charged wirelessly and also transmit wirelessly. But it's not yet clear in what direction this is going, and also unclear whether you could also augment them with compute or not. This was something that the authors asked themselves because they are kind of like into this distributed computing paradigm. And yes, but they have been actually shown some results in rats for collecting neural data, but it's like very early stages. But like the idea is actually quite old. All right. Then here, so this is kind of a bit like Neuralink. So this is here like layer 7 cortical interface. These are electrode arrays placed on the brain, so not in the brain. So it's minimally invasive and brain tissue is not damaged, and they are inserted through this slit in the skull, right? And then kind of rest on the brain and detect data here. And this is kind of what this might look like then, okay? And this also is like quite early stages, but also here, initial human studies have been launched. So this is here March this year. So it's not entirely clear, but this is also like a cool idea. And I guess Neuralink, of course, does something similar and has shown results, right? So this is definitely also an interesting route to go. All right, so maybe finally, so I thought about what about if we in some way hierarchically combine these methods? So maybe we could have a few more invasive and many less invasive ones and somehow get better results by doing this. And I would just ask you if you see any like potential or problems with this approach.
So the cons could be the cost to the structure and collecting and interpreting data from the two sources or multiple sources.
Mm-hmm.
Benefits could be a better resolution for whatever task that you may need to do. But before that, it's important to see if the task that you're trying to do with it really needs some sort of heterogeneity.
Yes.
Maybe another question would be, if we have, for what reason would we need this hierarchical design? If we already have super invasive implants that can detect high resolution data from all across the brain, why would we need ones on the outside of the skull that are not invasive, since we already have data?
Yes, so to that, I think the idea would be that like we can't do like a single invasive implant and detect everything from the brain, right? So we would maybe have like some spread out and then have more that cover other brain areas essentially that are less invasive to in total get a better coverage while having like something from each level. But yes, good points. So yes, so first of all, maybe we might need less fully invasive nodes if there are less invasive ones in the system as well, and reach the same amount of performance than with like as with many or more fully invasive ones. But it may, of course, be superfluous if a method at medium invasiveness works well enough, right? Like if something like these Neuralink or these on-the-brain kind of things that aren't that invasive can sense deeply enough that if you implant many of those, you don't get a lot of benefit from the invasive ones, then this might just not be necessary. Then also it will, of course, as you said, likely induce like massive complexity overhead to orchestrate. Like if we have all these different ones, like how do we compare these resolution? How do we put all these different puzzle pieces right in the full picture? So this is of course a big consideration. And then all in all, like the actual benefit is unclear, right? It's just like a totally exploratory idea. But yes, thank you for the contributions. So then the next point would be about the error resilience of signal comparison, which I mentioned in the networking part. And I will repeat part of this here. So the idea is to keep erroneous signals due to the natural resilience of signal similarity methods. So to not have to retransmit them. And this works with a bit error rate below 10 to the power of -5 and lowers the network bandwidth and latency. Now the question would be, how can this be further exploited? Do we have time? Okay. So yeah, so the question would be, how, if at all, can this be further exploited potentially for the system? And I would also like to show some related work on that. So for example, here, I think this is actually from Safari group too. Here they basically use approximate DRAM, which uses much less power, but isn't entirely accurate anymore, to like induce power savings and performance gains in deep neural networks by exploiting their natural resilience to errors, essentially, in their input data. Yes, and now basically same question. What about SCALO? Like anything similar or anything different that we maybe could do? Okay. So if there are no ideas, I will just present some of my own. Okay. So first, I thought that like in the spirit of this paper, oh, sorry, it's the wrong button. So in the spirit of this paper, we could maybe use an approximate NVM for the signal storing. So I mentioned that the NVM is partitioned into 4 partitions. What I didn't mention really is that these 4 partitions are like for hashes and application data and signals. So we could potentially use an approximate NVM, and there are apparently technologies for that, or these ideas for that, to store the signals and exploit also the resilience to that. But of course, well, first of all, the question would be, is it easy to combine? Do we need like a new memory module then in there? So like an entirely different component in the implant just for the signal storing? How feasible is this? I'm not sure, questions to ask, right? And then also, if we already have this approximate NVM and we have some errors from there, then also the question becomes if we can still tolerate these errors that we might have over the network, right? So can we then still keep signals that don't conform to the checksum, right? Or do we lose this property by doing that? And if we do, what's the trade-off, right? So what's better, what's worse, right? And then some less concrete ideas. So I thought maybe if a few errors in all signal packets are tolerable, which they kind of suggest, then we may be able to use some of the bits for other purposes while keeping probability of failure low. But there, of course, the question is if we say we can tolerate 10 bits and we use 5 for something else, and what if we use 5 correct bits, right, and just throw them away? Can we still tolerate this amount of error? How does this change the probability of a total failure in the signal comparison? Things like that. All right, and then in a bit of a similar spirit, I was wondering, like, why do they even use a checksum on the signal data if they don't care if the checksum is valid or not? So here again, I think one could either reduce the network load by just getting rid of the checksum, or also use these bits for something else, maybe for like a bigger signal size or similar things, right? More metadata, whatever. All right, and then finally, it's kind of like an open question. Any ideas for cool applications, maybe for brain-computer interfaces, just in general? Before I wrap the talk up.
Yeah, I mean, I guess in the medical domain, there's many ideas that are also like worth the trade-off. So, for example, I think there's also work ongoing on like treating, let's say, vision impairment or something like that. So that also includes like feeding information back into the brain, let's say from a camera or something. So,
yes, that's a very good point. Anything else? All right, so yes, I've just listed a few. Some of these are also like repeats from what I've mentioned earlier. So first, like monitoring and improving neuroplasticity and learning would be something. So yeah, also like, of course, it's very interesting to go deeper into these like heavily reliant on feedback methods, right? Because like movement and stuff like that isn't really like doing that a lot. And also tracking and improving sleep potentially. Then this is like a bit of a more out there thing, but like maybe we could somehow compare like brain functions between humans and animals, and maybe have like classifications for like similar intents and enable communication, like direct communication through something like this, maybe. I think this would be really cool. Then also restoring senses, right? Vision, potentially whatever, smell, taste. Also motor function, which isn't really a sense, but right, but maybe also haptics. But of course, you also need some like data collection device for this, right? Some sensors, like for example, like an artificial eye or something. Then improving memory and attention, treating neurological diseases, right? I already mentioned a few: Alzheimer's, Parkinson's, depression, addictions. Also this seizure detection and mitigation, which we've talked about, and yes, many more. So this is really like a huge area of potential, I think. And of course, applications in different fields, potentially like entertainment or things like that. Yeah. So thank you for your attention, and this was my talk.
Okay. Is that okay for you?
Yes.
Okay. Today we have 3 presentations, so the session could be extended to 7 p.m.
Test the mic.
Test.
And Zoom hear us? You say something again?
Hello, 1, 2, 3.
Okay, yeah, then I'll just assume it's fine. Okay. Okay, very cool. So I guess we will start with the presentation. Hello, everyone. We will start with the presentation on architecting PCM as a scalable DRAM alternative. Let's welcome Yanis. He is a first semester master's student at ITET. He's interested in computer architecture and operating systems, especially where the hardware and software comes together. Alongside his studies, Yanis also works part-time in embedded software, gaining hands-on experience with real-world systems. Yeah, let's welcome Yanis, please.
Yes, thank you for the introduction. And welcome from my side as well to the paper Architecting Phase Change Memory as a Scalable DRAM Alternative, which was published at ISCA 2009. Do I need to do anything to get the... All right. So to give you a high-level overview of what the paper is about, I'll start with the executive summary right at the beginning. So the problem the paper addresses at its core is the DRAM scaling problem. And PCM is expected to scale better to smaller technology nodes, but instead it suffers from high latency and also high energy as compared to DRAM. And we also have limited endurance. So the goal of the paper is to find architectural solutions to overcome PCM's major shortcomings relative to DRAM and make it a competitive alternative technology, which promises better scaling. And the main contributions from the paper are first, the authors survey recent PCM prototypes and derive a model which can be used in architectural studies. And they evaluate more or different buffer organizations, or specifically they introduce a more cache-like buffer into the PCM, which through increased hit rate aims to improve energy and performance of PCM. And the last major contribution targets the limited endurance problem, and the authors propose a mechanism to keep track of which data in a row has changed and avoid writing back data that has not changed unnecessarily to improve endurance. The results from a paper are first, they achieve a reduced performance degradation relative to DRAM from 1.6, which is a naive PCM baseline, to 1.2x. We achieve similar energy as DRAM. And lastly, a lifetime of 5.6 years on average throughout the benchmark applications. And in conclusion, PCM can be a viable alternative to DRAM and is a very promising technology due to its scaling potential. So now that I've given you a high-level overview of what the paper is about, let's get into more details. First, I will give you some additional background on the topic and some additional motivation. Then, to give us a good starting point, I'll talk about the baseline and its evaluation, which will naturally lead us to the key ideas. And after that, after a quick conclusion, I'll talk about strengths and weaknesses, and finally we'll have a discussion together. So let's get into some additional background. So what is the DRAM scaling problem, or why does it happen? So DRAM stores charge in a capacitor, as you might know, and this capacitor has to be large enough so that it stores enough charge to enable reliable sensing. In addition, the access transistor for the DRAM cell also has to be large enough so that the leakage currents are not too high, we don't lose data too quickly and have to do too many refreshes. So as you can see, things have to be large enough, and that's why scaling it to smaller and smaller technology nodes is a big challenge. And at the time of this paper, there were no manufacturable solutions known beyond 40 nanometers. And in general, it was known to be a very hard problem. So a natural question is, can another type of memory overcome DRAM's limitations? And to that end, the authors evaluated phase change memory. And how does phase change memory work? In this picture, we have a simplified depiction of what a PCM cell looks like. So squeezed in between two metal axes, we have a heating element and the phase change material. And by applying a current through the heating element and heating the phase change material in the correct manner, we can change its resistance. So if we add some peripheral circuitry, which might seem familiar to you from DRAM, we can see that the PCM cell in effect acts as a variable resistor. And we can, for example, encode 1 to a low resistance state and 0 to a high resistance state, apply voltage on the bit line, sense the current, and then we can figure out whether we have a 1 or 0 stored in the cell. How exactly do we need to apply the currents to change the resistance in the right manner? We can see that it's done through applying current poles. So if we focus on how to do a set operation, so setting it to a logical 1 to a low resistance state, this is done by applying I guess medium current and then slowly decreasing it, allowing the material to form or crystallization to occur, which leads us to a low resistance state. And if you can see that these dashed lines, in essence, could correspond to different resistance states, because if we cut it off more quickly, less crystallization occurs and we get a higher resistance. So we cannot only have a low and a high resistance state, we can also have some intermediate resistance states and use, for example, 4 states to have 2 bits per cell. And to set it to high resistance, we have to apply a quite high current and very quickly cut it off so that no crystallization occurs, and we end up with a high resistance. So what are the advantages of phase change memory over DRAM? So the key advantage here is really that PCM technology is inherently scalable. And in the paper, we can see this graph on the right, which shows PCM's linear energy scaling. So as we make technology nodes smaller and smaller, the energy needed to perform a write is expected to scale linearly. And endurance, although it is limited, where DRAM is considered to be not limited, it is expected to scale nicely as we continue to smaller technology nodes. The second advantage is that it supports multi-level cells. So we could potentially reach higher capacity as compared to DRAM. And it is a non-volatile technology, which means we don't need to perform any refresh to restore charge from time to time, as we have to do in DRAM, and thus it also consumes low idle power. Phase change memory also has a few major shortcomings relative to DRAM though. The first one here is access latency, and the authors derive a 12 times increase in access latency compared to DRAM and a 4.4 times increase in read latency. And additionally, writes cost a large amount of energy because the current you have to apply to melt the PCM material is quite large. So the authors derive over 40 times increase in write energy compared to DRAM. And lastly, we have limited write endurance, which happens because when we heat and cool down the material, the cells expand and contract, which degrades the contact. So now to give us a starting point, let's talk about the baseline. And before I talk about the baseline and its evaluation, I have to do a very quick aside on methodology. And the most important thing to know is that the authors use simulation, specifically a 4 gigahertz, 4-core superscalar pipeline, the 2-level cache hierarchy, and the DDR2 DRAM model that was modeled after a Micron DDR2 of the time. And lastly, the authors evaluate their mechanisms using 9 parallel memory-intensive benchmarks from 3 different benchmark suites. And these benchmarks were selected particularly for their high memory intensity. So we can actually see a difference when we replace DRAM with a PCM. The baseline is quite simple. So we directly substitute the PCM model for DRAM. And in this manner, the authors found the average 1.8 times decrease in application execution time or delay, and an increase in 2.2 times for energy on average throughout their benchmark. And you might be surprised that this sounds pretty good compared to the raw numbers of the underlying characteristics that I talked about before. If you remember, like 12 times write latency, over 40 times write energy. Why is this so much better? Is there anything wrong with the model? What's going on? Just to give you some insight. So even the memory intensive benchmarks have some computation mixed in. So it's not all just memory accesses. And secondly, writes need to happen a lot more frequently for DRAM, because in DRAM, the reads are destructive. So after we perform a read, we lose the charge that's stored in a capacitor during the read, and we have to restore it by performing a write. But because in phase change memory, the reads are non-destructive, so we do not destroy the resistance when performing a read, writes have to happen less frequently. So the particularly bad writes occur less often. We get better than expected baseline already. And lastly, for limited endurance, the authors found 525 hours on average throughout their benchmark application. So now we kind of know what we need to fix. We need to fix performance, energy, as well as endurance. And the key ideas aim to do just that. The first key idea is a reorganization of the buffer. So it's kind of like a small cache in the memory. And usually this is just one row, also a wide, but just one row. And to give you some insight into why changing things in this buffer organization might be helpful, the first observation that's important is that the number of array writes is really the number of evictions of dirty data. So every time we have a conflict in this cache, and we have to write back one of the rows, that's when you have to perform a write. So if we can increase the hit rate or reduce the conflicts in this buffer, we can reduce the number of array accesses, so we can hide some of the bad properties of the writes, like energy and performance. And the second observation is also that when we make the rows narrower, then we write less cells when we actually evict the row, because there's less data that we write at once. So it is less energy. And thus, the idea is to introduce more rows in that buffer or the small cache, but make them narrower to improve both, to improve locality and also energy. And the key idea to tackle the endurance problem is an idea called partial writes. And the idea is really just, or the observation for this idea is that not all bits in the buffer row have changed when it's written back. So it might be that only one word has changed. And then when we write back the buffer row, traditionally still everything in that buffer is written, and some of that is written unnecessarily. So the authors try to only modify the actually changed parts of the buffer row. And the third key idea is more of a guiding principle throughout the paper. It's not a mechanism like the other two. The authors only consider these organizations if they're area neutral, so they do not take up more area space than a DRAM in comparison. And this is important for memory manufacturers because area directly equals to cost. So let's get into the details about the buffer organization. Again, beyond just the write energy, making the rows narrower also reduces the number of really expensive sense amplifiers that are part of the buffer. So to sense the current, we need some circuitry that helps us do that. And this is quite expensive. So by decreasing the width, we need less of those. And this area that we save, we can repurpose it and build additional buffer rows. And these are built with inexpensive latches. So what this does is trading off spatial locality and opportunities for write coalescing in one row, which is negatively affected because we decrease the width, with increased temporal locality of having more buffer rows. So to enable playing around a bit with the buffer organization, add more rows, make them less wide, we have to do some changes to the memory architecture. Specifically, we want to be able to change the number of sense amplifiers without affecting the rest of the memory array, particularly like the width of the whole memory array. So we want to have so we might need to share some sense amplifiers among multiple bit lines. And to enable this sharing, we need to add some circuitry or particularly decoders to select the right bit lines to connect to the sense amplifiers. And secondly, to enable multiple rows, we need to add explicit latches and also some additional decoders to select the correct row in the buffer. So this adds some area overhead, but the insight here is that by reducing the number of sense amplifiers, we really save a lot of area, so we can accommodate these small overheads. So now we'd like to find what exactly is the best buffer organization. So we just try a few different configurations and see what we find out. And in this graph, first, maybe I should give you some more information about the graph. On the y-axis, we have the delay or the application execution time, which is normalized to the PCM baseline, which is just one wide buffer row. And on the x-axis, we have a row buffer width. And the different lines correspond to different number of rows. in the buffer. So red is for 1, green is for 2, blue is for 4. And if you focus on just having one buffer row, we can see that varying the width of that row barely affects the performance, right? So what this tells us is that the spatial locality that we have available in this one wide row is not exploited in this benchmark. And we can also see that as we increase the number of rows going from red to green to blue, we greatly improve the delay, but we also get diminishing returns beyond 4 rows. So that's why it's only until 4 rows in this plot. And the key takeaway from this evaluation is that increasing the number of rows in the buffer can actually significantly improve performance, right? So what is the exact configuration that performs the best? So in this graph, we have different configurations, and on the y-axis, we have energy, x-axis, we have delay. And an important note here is that all these points are area neutral configurations, so they don't increase the total area, except the PCM baseline, which is here. So it is quite on the top right, so high energy, high delay, and the DRAM baseline is over there. And so we really want to get from green to blue. And it can be seen quite clearly that this point gets closest, right? So specifically, that's 4 rows of 512 bytes in this evaluation. And with this, we achieve energy that's similar to DRAM, so it's on the same level in the y-axis. And we have a delay of 1.16 compared to DRAM. So we kind of close the gap between PCM and DRAM with this mechanism. And the takeaway here is that we achieve best performance at 4 rows, and we get 1.16 delay and equal energy relative to DRAM. So the remaining problem now is the limited endurance problem of PCM. And the idea here is that we can improve the endurance by performing writes only on the changed cells when we do a buff or when we evict the row from the buffer. How do we know, or how does the memory know which part of its row has changed? Well, we need to keep track of that. So we need to add some dirty state, and we can add this dirty state. So you can think of it, you probably know in cache configurations, to keep track of what has changed, we keep like 1 bit, the dirty bit. So we can keep this at different granularities. We can keep it for every cache line, or we can even keep it for every word. And technically we could keep it for every bit, but at the bit granularity, we would need expensive comparators to really figure out exactly what bit has changed. And at the word level or at the last level cache line level, we can keep track of it more easily. So that's the only thing the authors consider in this paper. So to give you a very, very simple example, on the top we have a cache, and on the bottom we have the PCM buffer. Let's say we have a write to the cache for this word, and then we mark it as dirty. And now the cache line is evicted. Beyond just the data, we now also have to transfer this dirty state to the memory. So this adds a little bit of overhead. And then we also mark it in the PCM buffer. And now this dirty bit really controls pass gates and makes sure that only the written word here, the modified word here is written back. So usually, or in the naive baseline, the other words part of this buffer row are also written, right? So we save some unnecessary writes here. Now, how good does partial writes perform? So on this graph, we have a expected lifetime or endurance in years on the y-axis. And on the x-axis, we have different benchmark applications. Yellow corresponds to keeping track of every word that has changed, while for the black bar, we keep track of it only for every cache line, so 64 bytes. And we can see that performing it at the word granularity improves endurance to 5.6 years on average here. And if you remember, the baseline was 525 hours. So we improved quite a lot, which tells us that only a few words are usually dirty on a buffer eviction. And unfortunately, we can also see that for some of the benchmarks, like this one, the endurance is still below 1 year. But on average, we get pretty good improvement. So it looks like a quite feasible number now. So in conclusion, I will just give you the executive summary again, but I will not go through every single point. So the offers really try to close the gap between PCM and DRAM to make it competitive and provide or make use of the improved or better expected scalability of PCM. And for that, the main contributions are a technology survey, which enables or future studies as well, where they derive a model for PCM, and they introduce quite simple, or they demonstrate that you can close the gap between PCM and DRAM with quite simple area-neutral solutions. And in conclusion, phase change memory can be a viable alternative, and we really have a high potential due to its expected scalability. So before I go into the critical evaluation, I will just give you some room here to ask questions if you have them. And if not, I will just oh, there's a question there.
Yeah, I still had a question. So I was wondering to what precision you can control the value. So you said that you can like store values, let's say in between 0 and 1. So I imagine like if you wanted to do, let's say, computation using this memory, it would be useful to control it more precisely. Do you know how precise the technology is there?
Well, in the paper particularly, the authors mentioned that beyond 2 bits, it probably becomes too hard. And I think it's also controlling controlling the exact resistance. And the big problem here is also that you have this process variation, right? So when we apply the same current to each cell, the resulting resistance might be different for different cells. And it can happen that they will move into the wrong resistance state, right? And there are papers, so the authors also cite 2 papers. And in those papers, one of the authors says they can support up to 16 different states, so 4 bits. But how far exactly we can get, I'm not entirely sure either. I'm not sure anyone knows. But this is like to give you an idea of the ballpark numbers what we are talking about here. Yes, there's another question in the back.
During the evaluation of the endurance, does the memory controller control wear leveling, or how do they map the data to specific rows and columns, and how do they evaluate the endurance? Do they take into account maybe a specific address could be accessed multiple times where the other addresses are not? How do they do it?
Good question. So in particular, if I remember correctly, the authors assume there is a perfect wear leveling, and how they evaluate performance is they kind of derive a model based on the memory intensity of the workloads and stuff like that. But for the exact details, I will have to refer you to the paper. Okay. Okay, then I will move on to some evaluation and talk about strengths and weaknesses. So strength of the paper, in my opinion, the biggest strength is really that it is an innovative paper, and it was one of the first papers that evaluated phase change memory as a DRAM alternative. So traditionally, or before that, most people were not considering PCM as a main memory technology, but more so as a technology for use on the side of storage on the side of storage technologies. So perhaps more as a SSD or flash replacement, or perhaps an additional layer in the memory hierarchy. So between DRAM and SSDs, due to its access latencies and other characteristics. So it was not expected that it is feasible to use as a main memory because of its worse characteristics compared to DRAM. So the authors really take an innovative approach, in my opinion, and challenge some of these traditional ideas. And the second big advantage of the paper is that it works on a very important problem. So the problem of DRAM scaling, or more general memory scaling, is a long or well-known problem, and a lot of people have worked on it. And in my opinion, solutions are only as important as the problem they're working on. So working on an important problem is a big strength. And if you go talk about really more specifically the contents of the paper, I think the technology survey that the authors performed and the PCM model they derive enables further studies as well. So it can help further research. So they do a lot of hard work of trying to figure out how exactly does the underlying memory technology perform. If you don't know that, doing architectural studies is really hard. So this is, I would say, very beneficial for further research as well. And the solutions are, or quite a lot of care is taken to make the solutions practical for implementation and also make them area neutral, in my opinion. And lastly, the mechanisms are pretty effective. So we get PCMs into quite competitive range of DRAM. And we can thus provide its inherent scalability with maybe a low cost. So for the weaknesses, I feel like I had to dig a little deeper and I need to explain a bit more. So that's why every weakness gets its own slide, but I actually have less weaknesses than strengths. It may look like more. So the first one is that I feel like this buffer reorganization is a more general idea and not particularly specific to phase change memory, right? So applying these optimizations to DRAMs could reduce the claimed performance improvements. So we really try to close the gap, right? But if we then apply those same ideas to improve DRAM as well, then the gap has not gotten smaller at all. And the authors actually do have a small part in the paper about this point. And their argument is that it is unfeasible or infeasible in DRAM to do this kind of buffer reorganizations because large engineering effort has went into the cells to get them working. So they particularly say that, their example is that for these size 6, like let's just call them size 6 DRAM cells, they have to do like little unconventional designs, like having word lines that are not word lines that are not like a power of 2 to increase the reliability. So they say, oh, you have the unconventional designs and do a little weird things to get it working reliably. So we can probably not do big reorganizations. At least that's how I understand the argument. I'm not entirely sure whether I've gotten it correct, but this argument seems not too convincing, at least for me. For example, the authors also mentioned that size 8 DRAM cells, a little larger, they're not that popular, apparently, with the DRAM manufacturers, at least at that time. But I wonder, maybe size 8 DRAM cells and applying the buffer organizations would be a better performing baseline. And I think for fair comparisons, you have to compare the best performing DRAM organization with the best performing PCM configuration, right? And lastly, I think an argument can also be made for PCM that they also need a lot of engineering effort. So designing the PCM is not easy, I would say. And to give you an example of some unconventional designs, I have read one of the prototype papers, and in this particular one, they say that only 2 bits per byte can be written simultaneously at the same time due to reliability issues. So this sounds like it's not that easy to get the PCM cells working as well. And to sum it up, in my opinion, it is not a particularly strong argument why buffer reorganization should be feasible in PCM, but not in DRAM. Right. And the second weakness is about the mechanisms. So they are dependent on the workloads. We have seen an example for partial writes. So we could see that depending on the workload, the expected endurance was very low, or like less than 1 year. And well, this is if your workload changes most words in a buffer row, then we cannot save anything because everything has been modified, right? Yes. And a similar thing is for the buffer reorganization. It's also a technique that aims to exploit locality in the access patterns. So if we have a workload without such locality, then it cannot benefit. And in my opinion, it might even slow down certain workloads because the bandwidth decreases with smaller buffer rows. So you remember we reduced the number of sense amplifiers, so we can sense less data or get less data with one read operation. So if we want to get the same data that we got with one read before, we may now have to do more than one read. So that's why the bandwidth might decrease. And the last weakness I could come up with is that the paper makes quite a few assumptions and predictions during the model derivation, which might or might not affect the how realistic the model is. And I have to make a quick note so that, in my opinion, most assumptions are very reasonable and authors provide good evidence for them and also citations and whatnot. And the model also does not need 100% accuracy to demonstrate PCM's viability, which was really the main goal. So take what I say maybe with a grain of salt, but I would definitely challenge some of the assumptions. And I think some of the assumptions might also really lead to different results if they are don't happen to be accurate, right? For an example, the multi-level cell or storing more than 1 bit per cell. In the paper, there's the implicit assumption that this does not affect the PCM characteristics like latency, energy, and endurance, right? But in my opinion, changing from 1 bit to 2 bits per cell will most likely increase latency and also energy for few reasons. If you're interested, I can go in more detail later, but let's move on for now. And really, if the model is not realistic, then the results and mechanisms built on top might not be either. And it is true that making assumptions cannot be avoided because there was really lack of data available. And so yeah, you really could not get around that. But in my opinion, doing some sensitivity studies or evaluating a range of characteristics could help a lot. So right now, what we know after this paper is that if you have 48 nanoseconds read latency, 150 nanoseconds write latency, you get these results. And if we had like results like, oh, as long as your latency is like in this range, we are competitive, then it gives more insight as well, and it would also make some of my doubts about the model kind of irrelevant, because now, oh, even if it's not quite accurate, as long as it's like in this range, we are good. So yes, before we move into discussion, or I actually have the slide here, basically I just want to open it for any thoughts or questions that you might have. So if you also have some improvement ideas or whatever, anything you want to discuss. If not, I will go on to some discussion starters, or maybe I will just give my opinions on some of these things as well. So the first question is, maybe you have some improvement ideas for the buffer organization. Anyone have some ideas? Then maybe I will just give mine. So I did not have too many ideas either, but the one observation I had is that this really introduces another level of caching, right? That was kind of not there before. So we have more, due to more rows, we have a little bit more flexibility. Before, we don't have a replacement policy at all, because there's only one row. You don't have the option what to replace. But now this adds some more options. So I feel like techniques for caches also apply here. So prefetching or different replacement insertion policies can all apply. Whether they make sense or not is a different question, but right. If there's nothing, I'll go to the next point. One question I ask myself is, when I read this paper, is like, wow, this sounds really good. Why does my computer not have PCM? Yeah, might you have some ideas what might hinder the widespread adoption of PCM?
Well, I mean, I would assume that it's probably mainly due to the limited endurance. As you said, that in this paper, they kind of assume they have perfect wear leveling. But if you want to have any kind of wear leveling like they do for like flash memory cells and an SSD, that adds a whole layer of tons of extra latency, which probably would make it then far less competitive with DRAM.
Yes, that might be, definitely is one of the reasons, I'd say. I did not list it here as one I did not think of. Any others?
How much of it is maybe related to manufacturing, or like lack of manufacturing techniques for PCM? Since I can imagine that like the layout of like the two metals and this one, I don't know if it was a crystal that had the special property, that the manufacturing of this sandwich thing is probably pretty difficult.
Yeah, you're right. And I did read some newer paper about like some recent progress in PCM technology. And there's a lot of, I think there's research also going on, and there's problems in PCM manufacturing. One of them is also related to the contacts, getting those working reliably, or you also have issues. That's maybe an issue that mostly limits multi-level cells, is that you have effects of like resistance drift. So the resistance in your cell, although it varies very slowly, it might still go up a little bit. So crystals can still form and your whole resistance might shift like slightly, which makes keeping the different, or adding multiple bits and like having to keep the regions for different states quite narrow makes it quite challenging. For this is one of the examples, but there's definitely challenges in manufacturing. And I will also say that you already have so much know-how in DRAM, right? And adopting a different technology is a very, very quite high barrier or starting barrier. So maybe I will share my thoughts. So one of the things I tried to figure out In the paper at the time we had 40 nanometers, not possible, right? And I was interested, so what does it look like now? And I would say DRAM scaling has probably been better than thought. So people have found good solutions to DRAM scaling. And I checked some of the vendor websites, and Samsung advertises their DDR5 at 12 nanometers. I'm not sure exactly about their definitions of what this 12 nanometers exactly corresponds to, but using the same source as the authors used for in the paper where they said 40 nanometers is not possible, in that source we're now around like 14, 15 nanometer. So still it went a lot better than expected. And secondly, economies of scale. This is, I guess, related to manufacturing. So you can really sell these chips, DRAM chips, very cheap because you can amortize the cost among a lot of sold units. While when you're starting with a fresh new technology, you might not have that many clients yet. And there's really, just a really high entry barrier into the business. And to find a footstep, PCM really needs to provide really, really compelling value over DRAM. So it cannot just be competitive, it has to be way better until so that people go through the efforts to replace DRAM with it, right? And yeah, we mentioned it already, PCM also is not without its issues. So that's everything I could think of. And for the next interesting question that I had is like, so maybe not every computer now has PCM, but where can we find PCM today already? So do you have some ideas where, or some niche areas where PCM might have found its place already?
I think because of the lower consumption, power consumption, and the scalability, it may benefit for the embedded system in industry or aerospace. Yeah.
Yes, you are correct. ST Microelectronics, they use PCM as part of their automotive, embedded automotive applications. So that's true.
Yeah.
Any other, yeah?
Maybe we can still see them in general purpose computing if we architect a hybrid storage system. If PCM can, PCM has a better scalability. So if you can combine the benefits of the two, it could still be a good solution.
Right. Yes, I think that's definitely an area where PCM could be very useful. I'm not sure whether there's any like commercial products right now that use that, but it's definitely a good idea. Yeah. So, right. The ST micro, so low energy embedded systems, we already mentioned that. And there was a commercial product made by Intel, and it was called Intel Optane or whatever. And it's on the side of storage class memory. So that's really the additional layer in the memory hierarchy that I mentioned. So we have main memory, we have storage, and like in between, we have storage class memory, or you could consider it like another cache. So it's like another cache for storage. This in between. Yeah. And they stopped producing that. I guess it was too costly. And the last one is that at this, I don't think, or there's commercial applications of this, but recently there's been kind of an influx of additional research papers to use PCM for processing using memory, particularly for machine learning, because these resistive cells, if you connect them in a crossbar array, you can kind of exploit Kirchhoff's laws to make like vector multiplications, matrix vector multiplications inside the memory. Yes, so that was it. Thanks for listening. And I guess, how are we in the time? Oh, good. Yeah.
Let's take 5-minute break, and then we will have the last presentation of this semester.
So we have the last presentation of this semester now, and our presenter is Philip Widdowson. He's currently in his fifth semester of the bachelor program at ETH in computer science. And he has many interests, but his major interests are in hardware design and finance. So he's going to talk about a work which shows unique errors in 3D NAND flash memory, and also characterizes these errors and proposes some mitigation techniques for that. So Philip, yeah, you can start.
Can you hear me well? Yeah, thanks for the introduction. Welcome to my presentation on improving 3D NAND flash memory lifetime by tolerating retention loss and process variation. This paper was published at the Proceedings of the ACM on Measurement and Analysis of Computing Systems in 2018. So let's go into the executive summary. First, the problem identified by the paper is that 3D NAND error characteristics have not been well studied as opposed to in planar NAND. In planar NAND, we basically would organize the memory cells in a two-dimensional grid, and in 3D NAND, we'd basically stack them on top of each other. So this is kind of how you can imagine it. So the first contribution of the paper is to characterize these errors. The first of which is layer-to-layer process variation. This is basically where, due to manufacturing differences and errors and imperfections, the errors across different layers differ, and this can result in up to 21 times greater errors in cells in one layer as opposed to in another. There's also early retention loss, which is a phenomenon where basically cells lose their stored value over time. And this can result in up to 10 times more errors 3 hours after programming, as opposed to if we were to read data right after programming. The last kind of error identified by this paper or majorly looked into is retention interference, which is where vertically adjacent cells influence the stored value in a given cell. And this is not seen before in planar NAND. The second contribution by the paper is to model the raw bit error rate, or RBER, and retention loss. The two models are the raw bit error rate variation model, where we basically look at the error rates on different layers. And the retention loss model is where we look at the impacts of early retention loss. Now, the third contribution is the proposed mitigation strategies. So for the first error source, they proposed LaVar and RAID, which basically is a method where you adjust the read reference voltage based on the layer that you're reading from, and you change the RAID mapping slightly. In Remar, we adjust the read reference voltage according to the retention time, and in Reac, we basically adjust the read reference voltage according to what vertically adjacent neighbor we have. So using these mitigation techniques, we can get an overall result of about 1.85 times greater, longer lifetime, or we can reduce ECC storage overhead by 79%, and this is on state-of-the-art 3D NAND. And we compare this to, again, the same chips, the same state-of-the-art 3D NAND, but only using regular RAID. So let's look at the overview. First, I'll introduce 3D NAND, then we'll go into the contributions, conclude, and kind of summarize them again, look at the strengths and weaknesses of the paper, and then go into discussion. Yeah, so the introduction to 3D NAND. So first, what are we trying to do? Well, we're trying to store bits, ones and zeros in each cell. Now, how do we do this? The logical value of a cell is determined by the threshold voltage. The threshold voltage is the voltage at which a cell activates. So basically, we change the voltage at which the cell activates by placing more electrons inside a cell. And this is basically what we do. And more electrons basically means we put a 0, or we write a 0, and fewer electrons means we have a 1. Yeah, so let's look at the exact structure of a cell. So this type of technology is used in planar NAND, so in two-dimensional NAND. And we basically have a floating gate, and this is sandwiched between two tunnel oxide layers, on the top of which sits the control gate. And then we have the substrate underneath. What happens is we apply a voltage to the control gate, and then a channel forms in the substrate, and then we can the cell begins to conduct, basically. The process node is basically 10 to 15 nanometers, so it's very small. This is basically a marketing term, but you can think of it as being quite small. Now for the 3D design, we basically have a charge trap cell, which is very similar to this design, but the charge trap, the substrate sits in the middle, and so it's surrounded by the oxide layer, and then that's surrounded with the charge trap, which is where we basically store electrons. As you can see in the image here, the small minuses are where we store electrons, and this is similar to the floating gate in the two-dimensional design. And surrounding that is another oxide layer, and around that is the control gate. So the same principle applies when we apply voltage to the control gate, the cell begins to conduct. Noteworthy is that even though the process technology node is larger, the tunnel oxide layer, so these gray layers, are still thinner in this design. So let's quickly look at the structure. So for planar NAND, we can see vertically is the bit line, and then horizontally we have the word line. Noteworthy is that the word line holds the most significant bit page and least significant page. This will be important later. Now, the 3D design, you can basically see it's this stacked on top of each other, where in orange are the word lines and blue are the bit lines. The bit lines also connect different blocks here, which are displayed in gray. So now concretely, how would we write to a cell? Well, as I said before, we basically want to change the threshold voltage, again, the voltage at which a cell activates. But in order to do so, we have to erase a whole flash block. This is because we can't just remove a small amount of electrons from a cell. We have to basically remove all of them. Now, the specific way in which we do this is we use Fowler-Nordheim tunneling, where basically we view electrons as a probabilistic cloud with a non-zero probability of an electron appearing within it. So as you can see here, this is the substrate, and this would be the charge trap, or for the 2D design, this would be the floating gate. And by applying a high voltage at the control gate, so the orange parts in these diagrams here, which would be to the right in this bottom image, by applying a high voltage there, we would basically pull these clouds through the oxide layer, which is a solid barrier, and it would have a non-zero probability of appearing in the actual cell, and thereby we would change the threshold voltage, storing a value. Now, conversely, if we were to erase, if we wanted to erase the cell, we would apply a strong voltage here at the substrate, and we would basically pull the electrons back out of the charge trap. So now reading. We're looking at MLC design, which is multi-level cell, as mentioned in the previous presentation. This means each cell stores multiple values. MLC typically means we store two values, which is what we'll be discussing in this paper specifically. So the basic way that this works is, since we're storing two values, we'll have four different states, ER, P1, P2, and P3. And the way we read those is that we will basically, we place electrons that we've written into the cell, and this changes the distribution, the threshold voltage. And because of inaccuracies when writing, it will basically have a probability density function that it can be described by. And this is exactly what this is. It's basically the probability of having this exact threshold voltage. You can kind of think of it like that. And to illustrate how we would read, let's imagine that we were to program the P1 state. So the threshold voltage would fall somewhere here. And then the way we would try to read is we could apply the VA, read reference voltage, to the control gate, if you remember. And then if we were to apply this, the cell would not activate, so it would not conduct, because the threshold voltage is greater than the reference voltage. But if we were to apply the VB reference voltage, then it would activate, and it would begin conducting. And this is basically how we identify what state the cell is in. Now we would also apply the pass-through voltage to all the other unread cells, and this basically lets them conduct along the bit line. So the value read will only propagate through the bit line to the sense amplifier when we apply the correct reference voltage to the read cell. So quickly looking at the errors that exist. We have process variation errors. These are basically due to imperfections in the manufacturing process. Retention errors, which basically are caused by charge leaking out of the cell, out of the charge trap over time. And then write-induced errors, which are a little bit less important, but I'll briefly mention them. They're mainly caused by wear-outs, which is where after program erase cycle, which is when we program a cell and then we erase it, as would be suggested by the name. Electrons basically can get trapped in the charge trap, and we can no longer pull the probability cloud out of the cell. And this basically is called wear-out. And this would obviously change the voltage, the threshold voltage of the cell over time. Read-induced errors are basically caused by redisturb phenomena. Recall that we apply a pass-through voltage to all unread cells, but this can also have a slight programming effect. So this also causes some errors. Basically, when ECC and optimal read reference voltage is applied, when these two can no longer give us correct data, is when we lose our data and can no longer recover it. So noteworthy is that the main ones we care about in this presentation are process variation and retention errors, because these are the most severe for 3D NAND. So this is what the paper looks at. So quickly, any questions perhaps that you have before we move on? No? Okay, good. Because it's good to understand some of this background. So moving on to the error characterization. So first of all, I would like to briefly mention the methodology. So the paper looks at state-of-the-art 3D MLC. So they look at basically cells that store 2 bits. Then they conduct all experiments at room temperature, so 20 degrees, and they randomly sample 27 blocks. They do this by modifying the firmware in the flash controller, and this allows them to basically change the read reference voltage in certain increments, and this allows them to basically discover the distribution that we mentioned previously of the actual threshold voltage of each cell. Yeah, and then also using this modified firmware, they can bypass ECC and get the raw bit error rate, which is just the error rate without ECC correction. And this is exactly what they use to characterize these error sources. They use the raw bit error rate, but they also basically use the optimal read reference voltage, which is a read reference voltage that gives us the fewest errors. So we would basically apply a read reference voltage here. And the one that gives us the fewest errors, we would move it left and right. And that's the one that we would basically look at when we're looking at the error rate. And also another evaluation metric is the actual distribution itself. So these are the real distributions. In black would be the distribution right after programming for each state. And then in red is after a little bit of retention time, so 3-day retention time, 10,000 program array cycles just to wear out the cell. So again, wear out was there to simulate use. And then 900,000 reads. And we note that the distribution of the threshold voltage is Gaussian, and that it shifts a little bit to the left due to retention loss. Also, probably noteworthy is that the data is scaled because they want to keep the anonymity of the vendor, because there's only one that they use. So let's look at the first error source, layer-to-layer process variation. So prior work has shown that it's impossible to basically produce identical cells from layer to layer. So we'd look at the top and the bottom layer, and basically they will not have the same exact cells. So the first observation we make after 10,000 program array cycles, this is just, again, as I said before, to simulate wear. We note that the ER to P1 errors and the P1 to P2 errors vary significantly across layers, as you can see in the chart here. This is, yeah. Here in the orange line are the P1 to P2 errors, which is basically where we mistake one state for another. So, yeah. And then the blue is where we have these sorts of errors for the ER to P1 states. The next thing we note is that the most significant bit and least significant bit error rates change significantly across layers. Here we see that this would be the top layer, and this would be the bottom layer. So you might expect that if the cells are all the same, they would basically be approximately a straight line here, but that's not the case. And then we also note that the most significant bit errors are much higher than least significant bit errors. Now, if you recall, maybe you didn't notice this, but in the way we understand these states is that the bottom two states are okay, I don't know if this works well anymore, but in the ER and P1 state, we store the same least significant bit, and in the P2 and P3 state, we also store the same least significant bit. So we just apply a voltage in between here, and if the cell activates, then we know it's in either of these two states. So we basically know the least significant bit. And if it doesn't activate, well, then we know it's in one of these, and then we also know the least significant bit. But the most significant bit is mapped differently. So we actually need two different read reference voltages. But if there's a lot of shift in these distributions here, then this would, as we can see, lead to more errors. Yeah, we also note that there are more errors in the middle layers. So from this slide, you can basically take away that layer-to-layer process variation is quite significant. Early retention loss. So in the paper, they analyze different retention times from 7 minutes to 24 days. This is as opposed to different papers or previous works that only look at 5 minutes. So you can clearly see the superiority of this paper. Now, what do we actually observe? Well, this is the same data here. Again, we use 10,000 program array cycles to wear out the the cells. And here we see in a time plot which is logarithmic, here on the time plot which is linear, we see the raw bit error rate follows basically a logarithmic trend, and it increases very rapidly right after we program, and it's basically consistently higher than for 3D NAND than it is for planar NAND. Yeah, and some of the causes proposed for this in the paper are that the tunnel oxide layer is much thinner in 3D NAND, and this is because basically we use the different technology allows us to do this, but this also has a consequence where now electrons can leak out much faster from charge trap design than from the floating gate design. And also, if you remember, the layers are stacked on top of each other, and the cells are the vertically adjacent cells basically share the same charge trap. So what can happen is the electrons from one cell can leak into another cell, and this basically explains some of this as well. So we note that the raw bit error rate increases quite rapidly after programming. Now, retention interference. This is exactly the phenomenon that charge leaks from a vertically adjacent cell into its neighboring cell at the bottom. And this basically, retention interference is specifically how this affects retention loss, and retention loss is charge leaking over time. Now, what the paper notes after 10,000 program array cycles is that for 3 different victim cells, so that would be this cell here, with 4 different types of neighbors, these are the different shades of blue, for the neighbor in the highest state, so this would be the state P3, which has the most electrons stored in it, the change in the voltage in the threshold voltage distribution is the smallest. So if you imagine shifts in the threshold voltage, it's the least when the vertically adjacent neighbor has the highest state. Now, the paper doesn't really explain this in detail, but my intuition would be that as charge leaks out of a victim cell, its vertically adjacent cell in the highest state also has electrons that leak into it. So it kind of replenishes some of the charge lost. And this basically recovers some of the shifts in the threshold voltage distribution. Now, also in the ER state, this is kind of the opposite, where we imagine that here we have fewer electrons, and the electrons would leak from the victim cell into the neighboring cell. So this would make this light blue bar stand out and be kind of worse, but would make the retention loss worse. So quickly summarizing this, we have layer-to-layer process variation, which is where due to manufacturing defects and imperfections, we basically have different error characteristics along different layers. And early retention loss, where charge leaks out of a cell and changes the value stored. Retention interference, which is basically how vertically adjacent cells change this early retention loss. Now, we must correct this somehow. We must find some sort of mechanism to tolerate these errors. And the paper proposes to build different error models and to implement online mitigation mechanisms. Moving on to the error models. So the raw bit error rate variation model. This chart might seem a little bit confusing at first, but let me break it down. Basically, the variation agnostic VOPT is an optimal reference voltage, which is found using previous methods for planar NAND, where there's also some process variation between different flash blocks. And this is basically the best read reference voltage that we can get that induces the fewest errors from flash block to flash block. Now, the variation aware VOPT is this plus an offset for the layer in which we read from. So if we apply this voltage to read different cells in different layers, we can categorize the error rate. So here you can see that this would be a very high error rate, and this would be a low error rate, and this distribution of errors across different layers is approximately gamma distributed. Now, if we use this variation aware VOPT, which is aware of the differences between layers, then we can see the average shifts to the left. So on average, we'll have fewer errors. And basically, this is the main takeaway from the slide. The retention loss model is basically, if we recall the threshold voltage distribution, what happens over time, as I said before, the P2 and P3 states shift left. So if we have the same read reference voltage, what could happen is that we misidentify cells that we originally programmed into the P2 state as being in the P1 state. And that's obviously bad. So what we want to do is we want to change the optimal voltage as a function of time. We want to lower it, so we want to shift it left such that we get fewer errors and we don't misidentify these cells that have been programmed to here as being in P1. So this is basically what these charts show. Yeah, and also we note that this can be modeled as a linear function of retention, of the logarithm of retention time, because this is on a logarithmic time scale. So this is the basically the goal is to make a simple linear model of this kind of phenomena online, and then we basically model the read reference voltage or the raw bit error rate or the mean and standard deviation of the threshold voltages themselves. And we do this as a function of the logarithm of time and of the program erase cycle count. And this orange formula here is basically a formula for the optimal read reference voltage, but we could do it for the raw bit error rate and so on. Additionally, this model is easy to compute. We just basically use least squares, and then thus it's well suited to online use in the SSD controller. Moving on to the mitigation techniques. Let me just quickly pause. Okay. So the first mitigation technique is LaVar, or layer variation aware reading, where we basically apply an offset. As we mentioned in the first model, we basically try to find the variation aware read reference voltage. And then we basically just tabulate this offset, which we find by shifting the read reference voltage, and then we just basically try to find one that induces the least amount of errors. And then we calculate the variation agnostic VOPT, which is the optimal voltage accounting for differences between flash blocks. And this is basically done with methods found in previous papers. Yeah, so there's basically very minimal overhead. There's no modification to the hardware that we do. There's very negligible, the latency of table lookup is negligible. It's on the order of nanoseconds. And this whole table with the offsets is constructed in the background, so we don't really incur very much overhead. Now, what are the actual results of using this method? Well, here we can see the program array cycle count on the x-axis. On the y-axis, we see the raw bit error rate. Using baseline, just the variation agnostic VOPT, and LaVar, which uses the variation aware VOPT, we can see that LaVar basically consistently outperforms the baseline, although it gets a little bit worse towards the higher end of the program array cycle count. Now, another way to mitigate some of these errors is a layer-interleaved RAID. Now, RAID is a pre-existing technique where we basically map the same MSB page or the same LSB page across different chips into one RAID group. And this is basically a technique where we use error correction to try and correct some of the errors. And then this basically accounts for differences between chips. So if one chip's really bad, then we can kind of use the other chips to correct it. Now, the goal of layer-interleaved RAID is to basically lower the worst case raw bit error rate. And we do this by grouping reliable pages with less reliable pages. So as we've seen before, most significant bit pages are more prone to higher errors as opposed to LSB pages. So we'd basically group those together as opposed to here, where we just only take MSB pages into one RAID group. Yeah, and so the way we do this is we change the mapping in this chart here, and we incur a small spatial overhead because we have to have some blank pages. Yep. And so what can we gain from combining these two methods? Well, compared to the baseline, which is just, again, the variation agnostic VOPT, we can see that using LaVar and RAID, we basically significantly outperform the baseline. And this is the main takeaway from this slide. Now, moving on to the retention Remar, the retention model aware reading, which basically means that we adjust the read reference voltage based on how long since, based on the time since we've programmed a cell. And we basically learn the retention loss model online, and the retention model was the second model we looked at. And the way they do this is they first try to learn what the voltage distribution is for each state, and then they periodically relearn it. And using this data, they construct the model online, and they also store the timestamp of when they programmed a cell. And then whenever you want to do a read, you look at the current time and you find the difference between the program time and the current time. And this gives you basically a way to look up and predict the optimal voltage to read with. The overhead for this is about 800 kilobytes for a 1 terabyte amount of data, which is quite small. So this is also quite good. And now the results that we can see are with increasing program array cycle count, the raw bit error rate is consistently smaller using Remar than the baseline, which is just a read reference voltage that ignores this phenomenon of retention loss. A bit of a formatting issue, but so basically from this slide, we can gather that by accurately tracking retention time and using the retention loss model, the raw bit error rate can be reduced. Now, Reac, which is the final mitigation strategy, this is basically retention interference aware NAC or NAC, which is basically a technique developed in previous works where the read reference voltage is adjusted based on the state of neighboring cells. And this is done in planar NAND, where basically the current cell can also be affected by horizontally adjacent cells because the technology node is so small that even horizontally adjacent cells can impact the threshold voltage. But in 3D NAND, we basically look at retention interference. So this is the vertically adjacent neighbors instead of the horizontally adjacent neighbors. So we adjust this NAC kind of technique a little bit for that. Now, the concrete mechanism behind it is very similar to Remar. We developed this kind of online model, and we basically just we include the fact that the neighboring cell is in such and such state, and this gives us a sort of optimal read reference voltage. Now, unfortunately, the paper didn't really find significant benefit to using this, but this is probably due to the fact that the technology node is bigger in 3D NAND, so these errors aren't as big of an issue. But because we want to scale memory eventually at some point, this will probably get much worse, and this is where the paper says, okay, we could probably use this in the future and actually see better results. So putting it all together, basically using the techniques that this paper presents, we can either get an 85% longer flash lifetime. Here we see the lifetime represented, or we look at the lifetime in terms of the program erase cycle count, because we basically want to write and erase the cells as many times as possible. And here we can see that the ECC limit is the purple line. And if we keep the ECC limit, we can basically just have more program erase cycles, or we can also reduce the ECC limit to here, which means we have to store less ECC bits. This is 79% less storage overhead, and then we can correct fewer errors, but we also get fewer errors. So this is basically the benefit of these techniques. Now, any questions?
So in one of the slides showing layer-to-layer process variation, you had a picture where on the x-axis are the normalized layer number, and then you highlighted in red where's top and bottom. How do the authors ensure that these rows, which are on the top and which are on the bottom, since as far as I know, there's other memory technologies where there's internal mappings such that the logical layer number, row number might not correspond to the physical one. How did the author know which row is on top and how are which ones are adjacent? Is the question clear?
Yeah. They don't really go into detail. They don't really talk about that in the paper. But what I can say is that the normalized layer number, this is just basically scaled. So in reality, they have 30 to 40 layers in the chips. But yeah, they don't really say how exactly they get this. So yeah. Any other questions? If not, we can move on. Oh, not too fast. So in conclusion, what's the problem the paper identifies? Well, 3D NAND has not been, the error characteristics have not been well studied. So what it does is it tries to understand and mitigate these. And it characterizes them, first of all, then it models them, and it also tries to mitigate them. And finally, they basically get this overall result, which we just mentioned in the previous slide, that they get 1.85 times longer lifetime or a 79% ECC storage overhead reduction with basically state-of-the-art chips. Moving on to strengths and weaknesses. So the first strength I identified was that basically the paper is very comprehensive and thorough. It's quite a long paper and is very detailed. As opposed to this, basically previous works don't go into much detail. The paper says that only 1 or 2 error sources are really looked into in other papers, and that yeah, they don't really do a very good job characterizing them. Basically, other papers look at the floating gate design, which is not really used in 3D NAND, but they do that anyway. And here we really look at the charge trap technology, which is the most widely used in the 3D NAND design. Another strength that I thought was quite important was that instead of just stating the problem it actually also proposes solutions, and these solutions actually work quite well. So it's not just, okay, we've done this, we've identified this big problem, now everyone go and solve it. They've actually proposed solutions. Another strength is that the paper is quite didactic, so it's very thorough. It explains things quite extensively, so it could even be used for by students for if they want to learn about how flash memory works. It even has a section on 2D NAND. Yeah, so the paper is also cognizant of the future. It basically forecasts the importance of the techniques and the errors that they characterize, because basically as the 3D NAND scales down, there will be more layers, and there'll be, we talked about MLC technology, which is where we store 2 bits in a cell, but there's also TLC, triple level cell technology. There's also QLC, where we store 4 bits in a cell. So you can imagine there are then 16 states, and you can imagine that if there's a small shift in the voltage distribution, this could lead to much more errors. And also, if you remember, Reac wasn't very effective in the current technology, but it could find use in future technology. Again, recall that this paper is from 2018. So actually, this is a bit of foreshadowing for the discussion. Now, some of the weaknesses that I thought were maybe important. The assumptions, where perhaps temperature is not exactly an assumption, but I thought it's important to mention anyway. They kept the temperature constant, so at 20 degrees. But it's important to know that temperature isn't constant in the real world, and also that the temperature does affect error characteristics. So I thought that it would have been important for the paper to mention it at least, but they basically don't, even though they say that they do a full characterization of everything, but it seems that they didn't look at temperature. What I found a bit interesting, is that the same authors published Heatwatch also in 2018 before this paper, and this actually characterizes the temperature, the effects of temperature on 3D NAND quite thoroughly. So I thought it funny that they write this whole paper before this, and they basically don't mention any of it in this paper that I'm presenting. Another limitation is basically that, as I said, they only randomly sample 27 flash blocks, and it's a bit of a small sample size if you think about it. And they only look at one vendor, even though they do say this is a limitation in the paper itself. So when they talk about the methodology, they say that although these are technically limitations, since they look at fundamental architectural problems, that they can basically generalize this. But I mean, I would say that we can't really know for certain unless we actually do this characterization. On various other chips and vendors. So another weakness is that, as I said before, that the paper didn't really explain retention interference as in depth. So it went quite in detail, it went into detail with process variation and early retention loss. But as I said, with the chart, it just basically said, this is the chart, and kind of figured out. So my proposition was that charge leaks, and then it replenishes some of the, so charge leaks from a neighboring cell, and it replenishes the charge lost over time. But it's unclear if that's actually what's happening, because I can't really evaluate it that well, because I don't specialize in this sort of stuff. So, I mean, this also kind of confused me a little bit. Are there any questions perhaps regarding that? Or any comments? If not, we can move into the discussion. So what do you expect has happened to error characteristics today? Now, as I mentioned before, the technology has scaled down, so there are more layers, and the technology node has become smaller. Do you have any ideas?
Yeah, I mean, I guess you already mentioned it, but I guess we could see due to the downsizing of the components, like this charge leakage increases.
Yeah, yeah. Any other things? Yeah, that's correct. Yeah, I mean, unfortunately, I didn't really find that much data concretely supporting this, but this is what I did find. So if we look at what we find in this paper, and we again consider MLC technology and 30 to 40 layers, the number of layers has increased. So if we look at 64 layer and TLC, so we store 3 different bits in a cell, so we have 8 different states here. We can basically see that the on this chart, we basically see a similar phenomenon where the voltage distribution shifts left, which is basically kind of similar to what we've seen here previously. And the retention loss here, which is weirdly enough on the right side of the chart. So here we see what happens after we induce program erase, after we program and erase cells. So we get sort of an increase of errors here, as we would expect from wear out. And then here is where we have retention time, but this is quite similar. If you look at the y-axis, it's quite similar to MLC. So for some reason, seems not to have changed that much, but I do know for a fact that with QLC and that with even more layers, because this is only 64 layers, with 100 layers and even 200 layers nowadays, that it does actually, the error rate does actually increase quite a lot. And the lifetime is significantly less. Yeah, so I presented some of the solutions that the paper proposed. Can you maybe think of other solutions? Well, I mean, I have a few solutions, but maybe I can give you a hint. If you think about DRAM, what do we typically do in DRAM?
Well, yeah, I mean, we refresh the data periodically. So I guess you could do some kind of, after some time, you could just read through all the blocks and check if the checksums still match, and if not, rewrite them to, like, depending on how many bits you can are mismatched from the checksum, for instance, try and repair it.
Yeah,
maybe.
That's basically one of the techniques. Yeah. Are there any other thoughts? If not, sorry.
But the writes cannot be in place, right? You have to write to an open page and then discard the page you want to refresh.
No, actually,
correct?
they are in place.
Okay, so you just directly write back to the same place.
Yeah, well, actually, it works a little bit differently, but we can get to that. Yeah, because my first proposal isn't that, so we can mention that in the slide or two. I mean, if there are no other thoughts, then the first proposal, which is actually neighbor-assisted cell correction, which is proposed for planar NAND, which, if you remember, Reac was kind of the optimization of that for 3D NAND, but NAC is still quite commonly used. This is basically where we condition the threshold voltage distribution based on the state of the neighboring cell. So here you can see that the sort of red distribution is if this neighboring cell was in the 1-1 state. Yeah, and then you can see that the optimal read reference voltage changes accordingly. So yeah, and the way you would basically do this was you would try to use ECC. ECC fails, then you would shift the reference voltage, and then basically try again. And then you'd, if it fails, you'd try again. You basically try again until you succeed, unless you can't, in which case your data is unrecoverable. Yeah, that's as far as I understood what this paper proposes. now onto the actual, actually, there's another way to solve this problem. Basically, there's this thing called dwell time, which is the time in between the program and the erase cycles. So as we can see in this chart here, maybe it's not that clear, but in the top chart, we have a dwell time of 64 seconds. And in the bottom chart, we have a dwell time of 8,192 seconds. So if you pay attention here, the black line is after programming, and the red line is after some retention time, specifically 71 minutes in both charts. You can see that the shift due to retention loss is smaller with a higher dwell time. So this is kind of this is something we call self-recovery. And if you notice in this chart, the line at the very bottom, so the one that has the fewest errors, is basically where you have the longest dwell time. So increasing dwell time basically reduces the error rate. I mean, I didn't look into too much detail why this is, but perhaps this is some food for thought, maybe somewhere where you could do your own research or look into the actual paper. Now, the results that this paper proposes, which is kind of using techniques similar to this, but also it adds more to this. Basically, you can see this in this chart where we, similarly to this paper, we improve lifetime of the 3D NAND. In this case, we're looking at planar NAND, but yeah, the similar, it applies to 3D NAND as well. Now, the actual refresh solution, basically, you program in place. So you would basically apply, you would do ISBP. So you'd apply you'd apply a voltage, and you'd try and basically slowly, incrementally increase shift the voltage distribution to the right. So if it shifts left and the reference voltage basically is wrong, then you'd basically try to shift it back. So that's basically the idea. Instead of, yeah, I hope that clears that up. Yep. Any other thoughts or comments regarding these proposals?
Maybe a follow-up question on this. So during normal writing, it is always suggested that you can only write to the open page because it causes disturbance to previously written pages. Why is in this time the in-place reprogramming not causing any read disturbance, or why is it okay to do it like this?
Well, it probably does, but we basically try to use ECC. So we try to error correct, and then we try shift. And then basically if we do too much wrong, then we stop. And if we can't recover the data, then we can't do anything. But I mean, if you want to know more details about that, I would suggest looking at this paper. Yeah. Yeah. Now, I mentioned this as a weakness, but
sorry, I just had a quick question. Sorry. Is periodic like data scanning not something that current flash controllers already do? Did they discuss that in the paper at all? I was under the impression that they already had some kind of way to repair.
Yeah, this is exactly this. Yeah, this is nowadays what we do. But since this paper is from 2018, I believe they didn't do that at the time.
All right.
Yeah. So as I mentioned in the weaknesses, I talked about how the paper didn't actually discuss temperature. So what do you actually think the effects of temperature are? And this is discussed in one of the in the heat watch paper. Take a guess.
Well, I would assume it increases the leakage errors.
Yeah. Any other thoughts? Okay, so you're in fact correct. If we program at a high temperature, which is what this chart shows, if we program at 70 degrees, we will basically increase the speed of retention loss. So we will basically lose electrons faster over time, which is obviously bad. Yeah, and this paper basically looks at 20 degrees, so this would be somewhere around here. Yeah. Can you think of maybe another effect of temperature? Perhaps less obvious, but nevertheless.
Well, higher temperatures increase resistance, so that might affect the voltages that you read out.
Yeah, could be. Okay, so what I basically found is that for higher temperature when we program, we can basically reduce the number of program variation errors. Now, if you recall, that for the LSB, it's the same in the bottom two states as in the and it's also the same in the top two states. So what we can do is we can program just the least significant bit, and then afterwards, if we want to program the most significant bit, we can basically read what the LSB is, and then basically change the voltage distribution according to what we want to program. But problems can basically happen when we basically read the LSB and we don't really understand, we read it wrong. And this is what we call program variation errors. And basically, if we increase temperature, then we have fewer such errors. Another thing is that lower temperature can increase the benefits of dwell time, of longer dwell time. So this chart basically shows retention time on the x-axis and the raw bit array on the y-axis. And you can see that the different lines represent different temperatures. So the kind of lightest red is programming at a higher temperature. We can see that up to about 100 or on the order of 100 seconds, higher temperature is better for raw bit array. And this is basically because we have fewer program variation errors. Perhaps it's noteworthy to say that we don't really consider program variation errors in this paper because we program everything at once. So we program the MSB and LSB at once. So we don't really encounter this problem. But this is definitely the case for TLC and QLC. And you can see when we increase the retention time that high temperature basically performs much worse, which is what we would expect as we've seen in the previous slide. Yep. Any thoughts regarding that? If not, then I will conclude my presentation. I hope you enjoyed it and learned something interesting. Yeah.
First of all, thanks for staying for so long. It's great that people are quite interested and provide a lot of comments and discussion. Second, I think these are really three strong presentations. I really enjoyed the last one.
Thank you.
You went into a lot of detail and you covered a lot of work actually.
Yeah,
we have done.
I had to condense
this
it
work
quite
really
a bit.
excites me still. I mean, there were some questions earlier, like, does this increase the read disturb errors if you do in-place refresh? Yes, it does. So in the paper, we propose until you get to a point where you cannot recover those errors with ECC, you do in-place refresh, and then you switch to remapping-based refresh. So, and this is actually implemented in flash controllers today. Actually, a lot of things that you covered in earlier papers, like neighbor-assisted correction, that's implemented in existing SSD controllers today. So existing SSD controllers do a lot of other processing, like LDPC decoding, etc., soft decoding. So this is a very fascinating area,
yeah,
where very little is actually exposed to the real world other than some of these papers and some of the other ones that you
Yeah, I mean, I mentioned that I couldn't really find that much research showing that QLC and TLC has a much higher error rate than MLC.
Yeah, it's unfortunate. I mean, you can find research at the device level. So if you go to conference like IEDM, Electron Devices Meeting, you will actually see device level research where people characterize these things, read disturbance, retention, etc. But at a real system level, research like this is lacking because it's very difficult to get access to the commands with which you can exercise, flash, build infrastructure, and get results. But I enjoyed your presentation. That's great.
Thank you.
Okay, I have more comments, but we don't really have time, I think. People are ready to go. But thanks a lot, everyone, for participating. Hopefully, this course inspired you to think big and maybe do research in some area, and you can have a lot of impact. Okay, thank you. Have a good break.
Can I quickly announce 3 things? I will use this one. So first, as you know, this is the last session of this semester, but you can still working on the feedback for all the presenters and your mentors until the end of this month. We may release the feedback later so you can learn from the feedback. Second, we will release the synthesis report soon. The deadline will be the beginning of the February, so you will have enough time to work on it. Third, if you are interested in working with Safari Group, please send me email. I know that we have collected this information at the beginning of the semester, but who knows, you may fall in love with some research area because of this course. I hope so. So you can, in this case, you can contact me or your mentors. I think that's all. Thank you for.
Feel free to email.
Yeah. Thanks for all your support. Merry Christmas and Happy New Year.